Well, what I'd like to do now is use a little visual demonstration thing to show you that the kinetic theory of gases really does support the laws that we've seen. And I've got this little device here that has the capability of moving several things. Here's an opening. I could slide the opening shut or open. There's a thermometer that can measure temperature. There's a little readout there. There's a pressure gauge. There's a pump that allows me to pump gases in here. There's a heat control, so I can add temperature or remove temperature. And then there's a little guy here that can make this box smaller or bigger. So there are all these things that I can do. So what I'm going to do first of all is I'm just going to put some gas in my container by pumping it in through this pump. So I'm putting these particles in there. And just like particles we imagine would do, like atoms or molecules would do, these things are jiggling around in constant random motion. And notice that the pattern is chaotic and random. There's nothing really going on here that's structured. They're just banging into each other and into the walls of the container. Now let's think about Boyle's law. Boyle's law requires that the temperature remain constant. So up here in this corner I have a little clicker that I can click that temperature stays the same. And then I'm going to adjust the volume and see what happens to the pressure. Now look at where the pressure gauge is right now. It says it's 1.0, it's just about 1 atmosphere. I'm going to take my little guy and make the volume smaller. Now Boyle's law would say that the pressure should go up if I make the volume smaller. Let's see if that actually happens. The pressure has in fact climbed to 1.39 atmospheres. Now the temperature went up too, but it's come back down. Now that it's come back down, it's still higher. It's not 1 atmosphere anymore, it's 1.18 atmospheres. Why is the pressure going up? Well, if you watch the little particles jiggling around, you notice that they're hitting each other and hitting the walls of the container more often. Pressure really is just the combined hitting of all those little particles. Since they're hitting more often, there's more pressure. So Boyle's law is explained by this idea of little particles in constant random motion. I'm going to back my little guy out again. Next I want to look at Charles's law. Well, Charles's law says that when I increase the temperature, the volume should increase if the pressure remains constant. So here's what I'm going to do. I'm going to click my little constant pressure box, and I'm going to add some heat. So the burner fires. Look what's happening to the little guy. He's getting pushed out. The volume has gotten larger because the particles are now moving faster. If the particles are moving faster, they're going to hit things more often. That would make the pressure go up, but the pressure can't go up. The only way it can keep from going up is if it has more space for the particles to move in before they hit something. So the volume has to get bigger, and we saw that happening in this model. Let's see what happens when we cool it down. Put some ice underneath there. Cool down the particles. Particles begin moving slower. That makes the pressure drop. So the guy has to respond by pushing it in so that the particles can increase their pressure. Oops, got a little too cold. Well, now let's look at Amundsen's law. Amundsen's law says that volume has to be constant, and when it is, temperature increase causes an increase in pressure. Now let's think through why would that happen. If I add heat, what's going to happen to the particles? They're going to move more rapidly. They're going to have more kinetic energy, each particle, because remember, it's proportional to the square root of temperature. So now I'll add heat, but the little guy can't move because volume is held constant. What happens to the temperature? The temperature rises a bit. I add more heat, temperature goes up a little more. Add more heat, the temperature goes up a little more. So the faster the particles move, the more heat is there, the higher the temperature is. I'm going to reset this. Now I'm going to try something different. I want to see if you can visualize Graham's law of diffusion based on the kinetic theory of matter. So I'm going to pump in some gas, and I have the heavy particles that I had in there before, and then I'm going to put the same amount of a lighter species in there. 2 pumps. Now I have 2 particles moving around in there. You can see if you're looking closely that the heavier blue ones are not moving as fast as the lighter red ones. Well, that makes sense because root mean square velocity is inversely proportional to the square root of molar mass. Now watch what happens when I create a little opening by sliding the lid part way off. 1 red escapes, 2, 3, 4, and finally I get my first blue. Reds escape at a pretty high rate compared with blues because they're moving faster, and because they're colliding more often, they will collide with the hole more often. So I'm going to lose more reds than I will blues. The rate of diffusion is faster. We've learned a lot about ideal gases, but real gases don't always behave the same way as ideal gases do. And that has to do with the fact that the kinetic theory of matter makes some assumptions that don't always work. Now, the kinetic theory is supported over a wide range of ordinary conditions, like we can see on this graph. PV over T is supposed to be constant for an ideal gas, and that's shown by the red line here. It's flat. No matter what the pressure is, the ratio of pressure and volume to temperature remains the same. That's the combined gas law. But real gases don't always behave that way. In this zone here, they're pretty close to the red line, but as the pressures get higher and higher and higher, real gases actually deviate from ideal gas behavior. Why do they do that? Well, one reason is because particles really do have volume. The kinetic theory of gases says that they don't. But if you start to smush gases into a smaller and smaller and smaller space, they start to actually show up as a significant part of the volume. Well, that's what happens. That's one way you can get to these high pressures, is by smashing this gas into a small space. And another reason that real gases deviate from ideal gas behavior is that real gases don't really not interact with each other. When they collide with one another, they actually stick for a little bit before they will release from their collision, and so they lose a little energy. When the particles are far apart, well, then that doesn't really matter that much because they'll regain the energy before they make the next collision just from the ambient temperature. But when they're close together, well, those sticking powers from the interactions become significant. How big the deviations are depends on the chemical properties of the individual gases. So real gases are all different. Ideal gases are identical, but when you get into the real zone, into those pressures and temperatures where ideal gas behavior breaks down, then it matters what gas you have. They're all slightly different. So what can you do about it? Well, one way to think about the fact that the volume of particles isn't really zero is to think about a container that contains a gas. So here's my little cylinder. It contains some gas. And for a real gas, I can think about it this way. I can think about this container as being divided into two parts. I'll make this part down here on the bottom a little cylinder that contains my particles. I'll call this VP for particles. And then the rest of this space, this larger cylinder up here, I'll call this V ideal. This contains the ideal part of the gas, the part that doesn't actually take up any space. So the total volume is going to be equal to the ideal volume plus the volume of the particles. Now for an ideal gas, we know that PV is equal to nRT. But this V here, well, that's our ideal V. But the volume of the particles, that's going to be dependent or proportional on how many moles are there. The more moles of particles I have, the bigger that space is actually going to be. So I'll make a constant of proportionality and turn this into an equation. I'll say the volume of particles is equal to some number B times the number of moles of particles that are there. And B is actually just kind of the size of a particle. But V ideal, if I think about it, is equal to the total V minus the volume of the particles, which means the ideal volume is equal to the total volume minus N times B, which is what we decided we were going to call the volume of the particles. So you can modify the ideal gas law in this way. Instead of putting ideal volume in there, we'll put in something that's realistic. And we'll say P times V minus NB, where V is the total volume, is equal to N times R times T. And that compensates for the fact that we have a real gas there. You don't have to use this very often, but when you're in those strange conditions where the ideal gas law doesn't hold, this is useful. But we have this other problem, and that is that we have collisions that aren't elastic. And there's another way. This is harder to understand where it comes from, so you'll just have to trust me on this one. You can also compensate for those collisions by putting this other factor in there. The pressure is actually increased by this factor, N squared times A, which is another constant of proportionality, divided by the square of the total volume. So you put this in for pressure, because that increases pressure, and our compensating factor that we have for volume, and you come up with this new equation. Pressure plus N squared A divided by V squared. We'll use that instead of pressure. And V minus NB we'll use instead of volume. That equals N times R times T. That equation is called the van der Waals equation of state. And it's just one of a bunch of equations that are used to kind of compensate for the fact that ideal gases don't behave like real gases. So in this van der Waals equation, this number, A, and this number, B, because they depend on chemical properties like interaction and size of particles, they depend on what gas you're using. So if you're going to use the van der Waals equation, you have to get a table that has A and B for particular gases and plug that number in depending on which gas you're working with. And then you can solve these problems. Not relevant to most people, but for some specialists that work in extremely tricky gas conditions, that would be important to know.